Time for us to do some more practice doing constrained optimization. In other words, we're trying to optimize, find a max or a min, or maybe at least where max or min could occur for a function, but there's some additional conditions placed on what we're willing to accept. Now, how do we do it? Well, Lagrange multipliers. And the idea is, two gradients have to be multiples of each other. That's the multiplier coming into play. And the way we really go about solving it is we get a nice system of equations. That means algebra. So yeah, a little bit of calculus to set things up, but algebra is what's going to bring it home, which means we need to be doing our practice. The more we practice, the more comfortable we get, and the better we are at solving these problems. So try to do as much as you can. If you're following along with the video, make use of the pause button. See a problem that you like, pause it, try it yourself, see how far you can get, and if you ever need me, I'm here, and we can talk about it. So let's work together, let's become wonderful, because I know you can. I know you can do this. You are capable and amazing. And let's begin. Our first problem. You run a non-profit organization which produces water filters, W, and X-ray machines, X. That's very good of you. I knew you were a great person. So, given your resources, you can make a combination of W and X that satisfy 3x squared minus 2xW plus W squared equals 144. Given that a water filter helps improve 1,000 lives, and an X-ray machine helps improve 3,000 lives, determine how you should choose W and X to maximize the number of lives that are helped. All right, that sounds good. Calculus being used for good? Definitely we approve of that. So let's think about what we have. We certainly see one equation. So our I gets automatically drawn to this equation right here, 3x squared minus 2xW plus W squared equals 144. Now the question is, what's that equation? And the answer, it's a constraint. Now how do you recognize a constraint? Well, normally if you see some relationship equal a constant, that's a constraint. So that's our constraint for our problem. All right, 3x squared minus 2xW plus W squared equals 144. And I'm going to think of this as G of XW. Now on a side note, you might say, whoa, can we go and use X and W for variables? Yeah, no problem. We can use any set of symbols we like. X and W are perfectly fine names for variables. All right, great. Well, what are we optimizing? Well, we look for things like maximize. Okay, that tells us what we need to optimize. And it says the number of lives that are helped. Okay, well, how many lives are helped? Well, it says, look, 1,000. Ooh, see, they were very fancy, and they wrote out numbers. So there's a 1,000, and for the X-rays, 1,000 for water filters, X-ray is 3,000. So we can say, look, our function that we're trying to optimize is 1,000 W plus 3,000 X. All right, great. We can actually simplify that and say, hey, hold on a second. Let's clean that up a little bit. Whereby clean it up, we mean, let's make it a little bit easier to work with. We're definitely in favor of making things easier to work with. Say, since both of these have a factor of 1,000, let's replace it with a new function that says, look, I just need W plus 3x. And that's perfectly fine. The only difference is that scaling factor of 1,000. But if I scale it, it's not going to change the optimal. It's just going to say, oh, I'm 1,000 times better than I thought. Great, perfect. Okay, so there we go. All right, we're going to sort of make a note here. Do this one, not that one. You might say, does it make any difference in the process? No, we just get to write a lot less zeros. Okay, so that was kind of the hard part. The rest of it is fun. So what's the rest of it? Well, we set up our system of equations. Gradient of f equals lambda gradient of g. Or f sub x equals lambda g sub x, and f sub w equals lambda g sub w. All right, well, we know how to compute these. You can say, well, f sub x, that's 3. So 3 equals lambda g sub x, that would be 6x minus 2w. And then on the other hand, f sub w is 1. All right, and that's equal to lambda and g sub w. All right, that's minus 2x plus 2w. All right, now, my piece of advice, when in doubt, solve for lambda. And even if you're not in doubt, solve for lambda. It works so well. So let's do it. And when we're solving for lambda, what we're really doing is we're finding new relationships between x and w. You see, we already have one, and that's the constraint. So if we find another one, well, then we have a second relationship, and that's enough for us to figure out where are the points that we're looking for. So we can say, all right, this tells us that lambda, if we solve, it's 3 over 6x minus 2w, but it's also equal to 1 over minus 2x plus 2w. Well, all right. Now, cross multiply. This becomes minus 6x plus 6w is equal to 6x minus 2w. And we can move terms around. And if we do that, we'll get 8w is equal to 12x. All right, wonderful. So now we have a nice relationship between x and w. In fact, we can divide both sides by 8. And we can say, look, w is 3/2 x. All right, because 12 over 8 is the same as 3 over 2. Just cancel a common factor of 4. So that's a really nice relationship. And we're going to take that now, plug it into our constraint, which is also a nice relationship. And between the two of them, we're going to get what we need. So, updating, what do we have? Well, now we can say, aha, 3x squared minus 2x times 3/2 x and plus 3/2 x squared is equal to 144. Notice what happens. 3x squared minus 2 times 3/2 is 3x squared. What? They cancel. Beautiful, beautiful, cool. So boom, boom. All right, so 3/2 x quantity squared is 144. Let's take the square root of both sides. And we'd have 3/2 x equals 12. Now at this point, you might say, whoa, Steve, you've done this to us before, Steve. You should have plus or minus, right? Well, okay. Well, let's come back to that. All right, so if we say 3/2 x equals 12, well, what is our conclusion? Well, our conclusion is we should say multiply both sides by 2/3. And if we do that, we'll get x, right? And so 12 times 2/3 is 24/3, which makes it 8. So we should have 8 of our X-ray machines. All right, well, now that you know x, great. How about w? Well, take 3/2 times x. 3/2 times 8, 24 divided by 2 is 12. So that says w should be 12 water filters. And there we go. There we go. Now, that was the only only solution we got, so that should be our answer. Now, there's a couple of things. How do we know it's a max? That's actually a really good question. And but it's also tied to another question which says, wait a second, Steve. Come back here. Why did you say it was 12? Why not negative 12? Let's do both at the same time. We could actually have set this equal to negative 12. And what would have happened? Well, if we did that, we could have said 3 halves x equals negative 12. And then we come to the conclusion that x equals negative 8. And finally, w equals negative 12. What does it mean to have negative 8 X-ray machines and negative 12 water filters? I mean, you can imagine that you send out somebody to say, look, I'm going to go out there and I'm going to start breaking X-ray machines and breaking water filters. Ah! And that's a terrible way to help people. That's doing the worst for people. You're definitely more detrimental. So say, okay, so we got 2 candidates, right? And this one, look, we're helping, what would we have? 12 plus 24, 36 times 1,000, 36,000 people. That's amazing. This would be harming 36,000 people. Now, but that still doesn't answer the question. How do we know it's a max? Well, okay, so I'm going to cheat just a smidgen. And it turns out that if you look at the set of points, 3x squared minus 2xw plus w squared equals 144, what you'll discover is that it's closed and bounded. It's an ellipse. It's a tilted ellipse. And so we know if we are in a place which is closed and bounded, we must attain a max and a min. And because we know we must attain one, and we got 2 points out, well, one of them is the max and one is the min. Now, if you're not satisfied with that, the other thing to do is say, well, let's look at perturbations. And one thing you could say is, let's throw all of our resources into just water filters. Okay, what if you did that? Well, if all your resources were water filters, you could make 12 of them. And that would help 12,000 people, but you could do more, right? Well, what if we threw all our resources into just X-ray machines? Okay, you could do that. And we want to get a nice whole number, but what would you get? X squared equals 144 divided by 3. That would be x squared equals 48. Well, that's about 4 root 3, something like that. But again, you can see you're helping less people. So the other thing you can do if you're not convinced about the ellipse, you can say, well, let's just try perturbations and see what happens. And that can help us out. But that's the details, right? All right. And for right now, we really want to focus not on too many details. We want to focus on process. And it's the figuring out what to do with the answer. Really, at the end of the day, the answer is just see what happens nearby. And that'll tell you what's going on. And of course, if you know something's closed and bounded, whew, you're safe. You're safe. And then whatever your points are, one of them has to be the max or min. All right. On to another problem. Use the method of Lagrange multipliers to find the maximum value of the function x to the 2/3, y to the 1/3, subject to the constraint x plus 4y equals 96. Oh, this looks good. This looks wonderful. Well, let's try it out and see what we have. Okay, so if we do our process here, we see, okay, that's what we're trying to optimize. Great. And we have our constraint. So this part is our function g of xy. Now, running through the process of setting up our gradients. Gradient of f is lambda gradient of g. So we have, all right, that really means fx equals lambda gx, fy equals lambda gy. Well, taking the derivative with respect to x, 2/3 x to the minus 1/3 y to the 1/3 is equal to lambda g sub x 1. And similar, fy, 1/3 x to 2/3 y to the minus 2/3 is equal to lambda, and g sub y is 4. Well, look, they're almost the same, right? The only difference is a factor of 4. Lambda versus 4 lambda. So if you multiply this by 4, then lo and behold, you get 4 lambda. This is 4 lambda. So those would have to match. So our conclusion, you get 8/3, and we'll write this as y to 1/3 over x to 1/3 is equal to 1/3 and x to 2/3 over y to the 2/3. Okay, so there we go. That's how we can rewrite that. Well, cleaning up, 3's cancel, cross multiply, and we'll get 8y equals x. Perfect. A nice clean relationship that we can use. Well, now that we know 8y equals x, and we also say, well, wait, x plus 4y equals 96. So, what is that going to tell us? Well, it becomes 8y plus 4y equals 96, right? Because this is our x plus 4y. All right, so 12y is 96, and that says divided by 12. Aha, y equals 8. Well, if y equals 8, then x equals 8 times 8. So that tells us x equals 64. And so we only get 1 point out. So that better be the maximum. Or rather, I should say, that should be where the maximum occurs. So the last thing to do, plug in. So we now plug in f of 64 comma 8. Well, that would be 64 to the 2/3 times 8 to the 1/3. And now we just have to be careful. The cubed root of 8 is 2. The cubed root of 64 is 4. But think of this as the cubed root squared. So it can be written as 4 squared times 2. Well, 16 times 2 gets us up to 32. All right. Now, is that the answer? Ha 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 ha. Now, okay, I should, in the interest of full disclosure, this is from an exam from not that long ago. Not that long ago. And seems pretty good. In fact, let's see if we can make it seem even better. If you think about what's going on here, say, okay, x plus 4y equals 96. It's really a line. And, well, okay, you can figure things out. For instance, it intersects here at 96 and intersects over here. Well, okay, 4 times y equals 96 would be y equals 24. And so we have the line that connects these 2 points. So, all right, so it's really trying to say what's happening on this line. And when we got this relationship, 8y equals x, well, that said, hey, there's this nice line. It's coming along here. This is our second relationship. And we found this point of intersect. We said, all right, what happens there? Well, we got the value 32. So our function, let me switch colors here so I don't confuse us more than we need to be. We want to be just the right amount of confused, right? So we got 32 at this point. On the other hand, if we move, we see, aha, when we hit one of the axes, we'll get 0, right? Because we'll have 0 to a positive number, 0 to a positive number. And so, all right, that's got to be a max, right? Because we're going down as we move towards 30. From 32, we go down to 0 or down to 0. So 32 is definitely a maximum. Is it the right answer? Well, if you say, let's just also throw in some additional constraint. So if we say, let's stick in the first quadrant, then we're great. If we didn't have those additional constraints, it's actually not the right answer. And what is the right answer? Well, if you look and you go in that direction, what's happening? Well, x is becoming a large negative number, y is becoming a large positive number. So if you have a positive number, take the cube root, that's positive, it's going to get bigger. A negative number to the 2/3 power is going to become positive and get big. So that says, hey, as you head off that direction, you're going to get huge. So the technically correct answer is infinity. Now, of course, nobody noticed this until well after the exam was made, and even then, okay, so what, how, why is that somehow missed? And the answer is, of course, you always have to be careful with Lagrange, and but the reason it got missed is actually a little subtle. Is as you pass through these points here, look at the derivatives. What do you notice? You get 0 in the denominator, which means the derivatives are really undefined. So there's no gradient at that point. So it's sort of like it breaks the system, and you kind of have to treat the pieces separately. So in the piece here, we definitely found the right thing. But compared to the other pieces, there's something a little bit more subtle going on. I fear this discussion might have the opposite effect of what I'm hoping to convey. So what I want to convey, I'll try one more time, but a little bit short. It's just be careful. Think about what's happening. You know, and you can say, well, let me just try some various points nearby to see what's happening, and what happens as I move away. And there's something strange going on with derivatives, because strange things can happen. And yeah, sometimes even calculus instructors, whoops, we can overlook things. So you want to be careful. You want to be careful. I actually do like this problem. We're just the minor technicality that it's not actually correct. But, you know, other than that, it's a nice problem. It's a nice problem. All right, well, let's keep going, right? More nice problems. The world is full of nice problems. So, a nice word problem. Here we go. You have made it into the championship episode of the Ultimate Extreme Happy Fun Roller Coaster Happy Fun Hour. You can tell it's happy fun. It even says it. Happy fun. Happy fun. Twice as fun. Good. You are now in the third round, the blackjack round, where you have to be the fastest in time to gain exactly 21 points, where points are earned by riding on 2 different roller coasters. There's the extreme, tumbler, and the Y won't it stop. Oh, that's rather convenient. There's X's and Y's. Cool. Because the roller coasters take different lengths of time to ride, the points are strangely distributed. Namely, if you ride the X, X times, and the Y, Y times, then your total score will be 2xy minus 3x. That is strange. Well, that's all right. It's reality television. You never know. It's always strange. As you watch the contestants going before you, you can't help but notice that they are dazed as they switch the rides, slowing them down. In particular, you observe the total amount of time the contestants ride the 2 coasters satisfies 2x plus 3y plus xy. Using the method of Lagrange multipliers, determine the optimal number of times to ride the 2 roller coasters to gain 21 points as fast as possible. All right, so we want to get to 21 as fast as we can. Great. So, where do we begin? On a problem like this, it's a little bit daunting, but now you say, okay, let's dig into it. Let's start by highlighting or underlining, whatever we have, anything that looks very mathy. And I see 21. Okay, I see an equation here, and I see another equation here. Those things jump out. Now, sometimes numbers are misleading, and sometimes they're spelled out. You know, there's things like 2 different roller coasters, but we say, okay, there's the x, the y. Let's see if we can put all these things together and see what's really being asked in this question. What is it that they're after? Well, remember, we have to get to 21 points. That's the score. And this is an equation for the score, 2xy minus 3x. So we need to get to exactly 21. See, it says the word exactly. And we say, all right, well, if we need to get exactly 21, that says we need to have 2xy minus 3x equals 21. This is our constraint, right? Because it's our function of xy equal a constant. All right, good. We've identified the constraint. Now, here is an amount of time. Now, we don't have a fixed amount of time, but we can say, look, we want to do it as fast as possible, which means we're trying to optimize time. So we're trying to optimize this function. F of xy equals 2x plus 3y plus xy. Now we're ready to begin. We have the function we're trying to optimize, we have our constraint identified, and we're perfectly set up. And now we're like, wow, so almost all of this was just wonderful, detailed story. Yes, the math is very compact. And you say, when sometimes you translate into math, like, wow, that's so much more direct and clean and concise. Well, that's one of our goals. We want it to be very clean, precise, and short. Easy to use, easy to understand. That's math, right? Easy to use, easy to understand. So now we have to stop and say, all right, where do we go? Well, it's the process. We know what process says Lagrange multipliers. So we're going to use the process. And so we set our partial derivatives. Fx equals lambda gx. Fy equals lambda gy. All right, well, what does that become? So f sub x, 2 plus y, right, 2 plus y equals lambda g sub x. Okay, well, 2y minus 3. All right, great. And f sub y. All right, 3 plus x. And what's true about that? That equals lambda of g sub y. Well, that's 2x. All right, wonderful, wonderful. Well, where do we go from here? Well, when in doubt, solve for lambda. All right, so we say, look, what is lambda? Well, in the first equation, it's 2 plus y over 2y minus 3. In the second equation, 3 plus x over 2x. And now cross multiply. So cross multiplying, what do we get? We end up with 4x plus 2xy is equal to 6y. Whoop. Now this is going to be a little bit tricky, right? So here it's just simple, 2x times 2 plus y, so 4x plus 2xy. Here, well, okay, so we're really taking 2y minus 3 times 3 plus x. So that's where the 6y came from, plus 2xy, all right. And now minus 9 and minus 3x. So that's the result when we cross multiply. And this one, you're like, it doesn't look like it's getting better. But wait, what do we see? Aha, good news. You see, if you've lived a good, clean algebra life, things should happen that are nice. And the 2xy's here cancel. So, what can we say? Well, at this point, we can move things around ever so slightly. And for instance, we can say, look, add 3x to both sides. Okay, sure. And we'll get 7x is equal to 6 times y minus 9. All right, so that gives us a nice relationship between x and y. But we already have a nice relationship between x and y, namely this relationship. So we can choose. Well, I can replace all the x's by y's, or it looks like it might be easier to replace all the y's by x's. So let's do that. We could say, hey, 6y, that's 7x minus 9. Or, sorry, excuse me, plus 9. Right? So we just add 9. Now we begin. What do we need to do? Well, how can I get a 6y? Well, I see a 2 times y. So, okay, if we were to multiply our constraint by a factor of 3, we could say, hey, 6 times xy minus 9x equals 63. Right? Right. Okay, so 6y I can replace by 7x plus 9. So x times 7x plus 9 minus 9x is equal to 63. Now, what happens next? Well, this becomes 7x squared plus 9x minus 9x equals 63. The 9x's cancel. Oh, they really care about us. The x squared I can divide by 7. So that says x squared is really 9. Wow, great. Well, x should be 3. We know it can't be negative because I can't unride a roller coaster. It can't be like, well, I got on my roller coaster, but I didn't have a good time, so I'm going to unride that roller. No, you can't ride a roller coaster a negative number of times. So we have the natural constraint of the problem tells us we can only take the positive one. We say, all right, well, that's x. What about y now? Well, 6 times y, that's 7 times 3 plus 9. 21 plus 9 makes 30. All right, divide by 6, and we get y equals 5. Okay, so we really end up with one candidate. And for us, our purposes, we'll say, that's enough. We're going to say, all right, x equals 3, y equals 5. That's the optimum. Because it is, in some sense, where an optimum potentially occurs. And because we only have one candidate, I'm going to say it must be, this is our candidate. All right. So what do we do? Okay, so we're going to do 3 times for the x stream. And we're going to do 5 times for the y won't it. And that's it. That's the answer. Wow, good. Now you know, before you go on to those reality TV shows, make sure you brush up on your multivariable calculus. You never know when it can come in handy and help you win. Because, that's what our goal is, right? Winning at life? Well, start by winning at calculus and being able to solve problems. So, there we go. Well, let's try another problem. Find the maximum and minimum values of the function xy, given that 16x to the fourth minus 32xy plus y to the fourth equals 256. Now, I want to tell you before we start, I really like this problem. And not just because I wrote it. I mean, I'm sure other people have written very similar problems. But one of the things that people often sort of roll their eyes at with Lagrange multipliers, like, okay, we can do Lagrange multipliers, but we could have just used our constraint to reduce the number of variables, couldn't we have? And we kind of go like, well, technically, But this is a time where it's like, forget it. Hopeless. This says, do you know how to solve for x in terms of y or for y in terms of x? You'd have to be able to solve a quartic. And it would be, yeah, sure, there's a formula for it, but forget it. Nobody has that memorized. Yeah, it's written down somewhere, but nobody has that memorized. It would just be impossible to work with. Ridiculous. And then you have to take the derivative of this insane expression. No, it's not going to work. So this shows you that, yes, there are going to be problems where, oh, Lagrange multiplier actually steps in and helps where other techniques will have you pretty much stumped and not able to make progress. And I will say that in some sense we're really doing the very basics of Lagrange multipliers. Of course, the further you go, the more elaborate you get, more variables, more constraints, then it becomes clear that yes, there really is power in this tool. And so don't underestimate our tool and appreciate it. Enjoy it while we can. All right, well, let's start this problem. Now, of course, I should point out, it doesn't even say Lagrange multiplier. How do we know? Well, we know we're trying to do an optimization. Okay, that's a giveaway because it says max and min. That means optimization. And we see phrases like given that. When you see given that or such that, really it says, hey, there's this constraint here. And when you see an optimization with the constraint, that's Lagrange multipliers. So this expression here, 16x to the fourth minus 32xy plus y to the fourth, this is our function in terms of our terminology, our g of xy. So where do we go? Well, we can say the following. We do what we always do, right? We write our equation. Fx is lambda gx. Fy is lambda gy. All right. Well, f sub x. Why? Well, because we need it. No, it's y. Oh, yeah, you're right. It is y. Yeah, okay. So y equals lambda g sub x. 64 x cubed, and then minus 32y. All right, interesting. Fy, well, that's x. That's lambda gy. All right, that's minus 32x plus 4y cubed. Okay. Well, I don't know about you. I'm feeling some doubt, so I'm going to solve for lambda. All right. Well, let's see. We get lambda is y over 64x cubed minus 32y. And you also have what? That's equal to x over minus 32x plus 4y cubed. All right. Well, what's going to happen? Well, now we're going to cross multiply, get rid of fractions, and hopefully, if we've lived a good, clean algebra life, and they didn't mess anything up and set up the problem, I really hope it's not, because it's a nice problem, then things should happen. So, cross multiply, what do we have? Minus 32xy, and then we're going to get plus 4y to the fourth is equal to, okay, 64 x to the fourth minus 32xy. Ah, beautiful, beautiful. And you see, there's cancellation. The 32xy's, they cancel. Aha, woohoo, nice. We can even go a little bit further. We can say, okay, well, I can divide both sides by 4. So we could say y to the fourth is equal to 16x to the fourth. And now let's just get rid of the fourth powers. So if we take the fourth root of both sides, what do we end up with? Now it turns out 16, not just any number, very conveniently chosen. 16 is 2 to the fourth power. So we end up with y equals 2x, right? 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 I think you're like, no, I don't think so, Steve. There's a suspicious gap here. There is a suspicious gap. A fourth root is a lot like a square root, right? In that when you take something to the fourth power, the sign gets lost. It's the difference between even versus odd powers. When you take a number to an even power, it's always positive, so you lose the sign. When you take a number to an odd power, you don't lose the sign. So when you take a fourth root, you have to be careful because you said, well, there may have been a sign thing happen. So it's actually plus or minus 2x. So there's two possibilities. All right, well, time to explore our possibilities. That's all right. We have plenty of time. Plenty of time. So let's start with y equals 2x. So we're going to go into our equation and put in y equals 2x and clean it up and see what we get. So, all right, so we have 16x to the fourth, then minus 32x times 2x plus 2x to the fourth equals 256. Well, we can combine, right? 16x to the fourth, this will also be 16x to the fourth, which will make it 32x to the fourth here, minus 64x squared, and bring the 256 across. Minus 256 equals 0. Everything is powers of 2. In fact, everything's a multiple of 32. So let's divide up by 32. Now, at this point, you might be saying, this looks like a fourth degree polynomial because it's a fourth degree polynomial, right? That's a good reason to say it. But it's also kind of like a quadratic, right? Because look at the powers, x to the fourth, x squared, and 0. So I'm going to do two things. First, divide by 32. But the other thing is I'm going to say, hey, this is like x squared squared, divide by 32, don't forget that, 2x squared, and then 256 divided by 32 is 8. And now we're like, wow, beautiful. So if I'm thinking of it in terms of like x squared, I can factor it. So how would this factor? Well, we would need two things that multiply together to give us negative 8, but added together to give negative 2. So what would do that? Well, I think negative 4 and positive 2 would do that, right? Let's check. X squared times x squared, right? Minus 4x squared plus 2x squared, minus 2x squared, and minus 8. Okay, so this says, looks like x squared is either negative 2 or x squared is 4. Now, one of these we can eliminate really quickly. We don't even have to consider anymore. Negative 2, we can't have x squared be negative 2. Forget that. Silly. Okay, which means x squared equals 4. All right, great. So taking square roots, you get plus or minus 2. Now, remember, we're in the y equals 2x camp. And so if I'm going to make a list of our points here. So we have 2. 2 times 2 would make it 4. So 2, 4, and similar, negative 2, and, negative 2, negative 4. That's a really badly drawn negative sign. Okay, so those are 2 points that come out from the Lagrange multipliers. One other thing I should have pointed out is it's not so clear. There will be a max and min, and normally in a problem we would make it abundantly clear that there is a max and min. And you might be worried, well, will we really find one? Knowing that there isn't a max and min actually gives us tremendous advantage. We just have to figure out where it can happen. All right. Now, that's if we take y equals 2x. What happens if we take y equals minus 2x? It's going to be very similar. So, okay, still 16x to the fourth, and then minus 32x times minus 2x, and then it'll be plus minus 2x to the fourth equals 256. Well, what changes? There's just one thing that changes. See, that minus 2 to the fourth, it's still going to leave us with 16x to the fourth, so that still leaves us with 32x to the fourth. The change is now minus 2 times minus 32 plus 64x squared, and then minus 256 equals 0. So again, divide by 32, x squared squared plus 2x squared minus 8 equals 0. And so this also factors, but now slightly differently. We need to have two things that multiply to negative 8 but add to positive 2, which would become x squared plus 4 and x squared minus 2. All right, well, that leads us to two possibilities. X squared is negative 4, or x squared is positive 2. Again, we can say it can't be negative 4. Ha! Silly problem. Out. So x squared needs to be 2. All right, well, that tells us what? Well, it tells us, hey, that says x is plus or minus square root of 2. So on our list, we have square root of 2, and then, remember, you have to multiply the y by negative 2, so minus 2 square root of 2, and then minus root 2, multiply that by minus 2, becomes a plus 2 square root of 2. All right. Whew. Now, here we go. We've took our constraint, used Lagrange multipliers, and said there are 4 potential points on our constraint for which we have gradient of f equals sum of gradient g. And those are the places where the max or min can occur. So we've identified where, the location, the locale of where things are going to happen. But we're after the actual values, the maximum and minimum values, which means we're not done yet. We need to do one more thing, which is plug things into our function. Now the great thing is our function is really, really easy to work with. It just says multiply x and y together. So we say, all right, if I plug in 2, 4, hey, that gives me 8. If I plug in minus 2 minus 4, it still gives me 8. If I plug in square root of 2 minus 2 square root of 2, well, the square root of 2's combined to get a single 2 times a minus 2 is a minus 4. And here, same thing. The square root of 2 is combined to give a 2. There's already a 2, so there's a minus 4. So we say, aha, here we go. The max value is equal to 8. And we can even say this is where it happens. It happens in 2 places. And the min value is equal to negative 4. And again, it happens in 2 places. And we're done. Wow, beautiful. Now, I know you look at this problem and say, wow, this is so beautiful. How can I become a math major? Okay, maybe you don't say that. But sometimes you look at these problems and say, I probably could have guessed 2, 4. Why did I need to do all this? Well, you could have guessed 2, 4 because the problem was set up to be a nice answer. But not every problem you're going to encounter is going to be nice. Nature has a very finicky way of throwing interesting problems in your direction. But the other thing is, you probably would not have guessed something involving square root of 2's. So though you may have guessed some cases, you may not always guess all the cases. So be careful. Don't rely on guessing. Don't get me wrong. I love guessing. It's a very powerful technique. But it shouldn't be your only technique. If the only tool you have is guessing, you're in trouble. Because some things just can't be guessed. You got to work the problem. So it's important to be patient. It's important to work the problem. All right. Well, let's keep going. That was such a good problem. I'm going to miss it. Our next one. Use the method of Lagrange multipliers to find potential locations of local maximums and minimums of the function. And it's f of xy equals 2 root 2x plus y, given at x to the 4th plus x squared y squared equals 48. Now it's being very cautious and hedging the bets, saying it's potential. We don't even have to figure out what the function is doing at those points. We're not going to worry about it. The reason it's being so cautious is the curve is kind of a strange curve. It's not impossible to plot it, for instance, you really can essentially solve for y. And what you'll see is it's not bounded, and you have some very unusual things going on. And whenever you have something where the inputs, well, they're unbounded, okay, strange things can happen. So we're going to say, let's avoid the strangeness, and let's just figure out what's going on here. Well, we know the method, Lagrange multipliers. It's given to us. Even if it wasn't given to us, we can say, okay, we see words like max and min, which means optimization, and we see this phrase given that, which means constraint. All right, so that definitely, okay, Lagrange multiplier, no problem. We see it. So here, we'll call this a name of a function. We'll call it g of xy. Now, don't get too caught up on using g of xy. It's just simple convention. And it's good to have a convention for convenience, but it's not one that's forced on us. We should be flexible. Remember that. Mathematicians are highly flexible. We're willing to change things on a moment's notice and say, all right, let's just call things something else. Okay, so our process, fx equals lambda gx, fy equals lambda gy. All right, well, fx is pretty straightforward. 2 square root 2 equals lambda gx. Not so straightforward. 4x cubed plus 2x y squared. All right. Fy, 1. Ah, nice. That equals lambda gy. All right, that's also not too bad. 2x squared y. All right, well, solve for lambda. So what do we have? Well, we get that lambda. And the first one, that's 2 root 2 over 4x cubed plus 2x y squared. It's also equal to 1 over 2x squared y. All right, well, let's cross multiply and see what we get. So cross multiplying here, we get the following. 4 square root of 2 times x squared y is equal to, and here we'll get 4x cubed plus 2x y squared. Now, before we go much further, let's stop and ask ourselves the question, can we divide to cancel? And why are we okay to do that? Looking at this, when we say, can we divide to cancel, all these terms have an x in common, x, x, x. Then we say, if they all have an x in common, let's just divide out, and then we're done, and aha, well, at least we simplify, and life is good. But are we allowed to, and why? Okay, the answer to the first question is, yes, we are allowed to. But it's more subtle than you think. Well, or maybe it's not. What's the key? The rule of thumb is you can divide to cancel as long as you're totally 100% confident I'm not dividing by 0. So if you can look at it and say there's no way I'm dividing by 0, go ahead and divide to cancel because you're going to be great. Can x be 0? And why not? Suppose x were 0. You'd have 0 plus 0 equals 48. So we know x cannot be 0 for our constraint. So that's why we're okay. We're okay if we divide through by a factor of x, because we're not going to lose anything. All right. Now, if we hadn't done that, the other thing we could have done, move everything to one side, pull out a 2x, and we say, oh, wait a second, you can't have x equals 0. Ha, 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 ha. Nonsense. Okay. At some point or another, you would have to address that. Here we were okay, but sometimes you're not okay. So be careful. Be the right amount of careful. Okay, so following through, I'm going to divide by 2x. And what happens? Well, we get the following. All right, so 2 root 2 times xy is equal to 2x squared plus y squared. All right, well, that should be interesting. Okay, that's not so clear what's going on. But that's all right. We like to explore. Let's move this term across. So that would say 0 is equal to 2x squared minus 2 root 2 xy plus y squared. All right, well, can we do anything here? Now, at first glance, it might not feel like we can, but they gave us this problem, so let's believe in them. They believed in us. They gave us the problem because they thought we were good enough to solve it. So we're going to show that they were right. So let's think about what we can do here. What we have is a quadratic. See, because I put the xy in the middle, right? Because it felt like, oh, this is x squared, this is y squared. This would be like the middle term. And you might say, well, could we factor it? And it might help to say, hey, you know this 2x squared? It's the same as the square root of 2 times x squared. Now, what do you see here? If this is a squared, this is b squared, this would be 2ab in the middle. That doesn't just factor. This is a perfect square. What? It's square root of 2 times x minus y, quantity squared. Wow. Cool. Wow. That is cool. Whoever comes up with these, they must have a lot of fun. All right. You can check this, right? You know, if you square the first term, a squared, that's your 2x squared. 2ab, so minus 2 root 2xy, and b squared, y squared. Okay, so, cool. And, well, take the square root. The nice thing is it's equals 0, so you end up with the conclusion, y has to equal square root of 2x. Well, that's a wonderful relationship. Now let's take that and plug it into our constraint. So, what does that say about our constraint? It becomes the following. We get x to the fourth plus x squared times square root of 2x squared equals 48. Well, okay, if we square that, that'll be 2x squared times x squared makes this 2x to the fourth plus another x to the fourth. All right, so 3 times x to the fourth is equal to 48. Divide by 3, we get x to the fourth is equal to 16. Nice. Oh, what's coming? Take the fourth root. Be careful. When we take the fourth root, what happens? Well, we're going to get 2 possibilities, plus or minus 2. And fourth root is actually kind of a nice number when we talk about 16. 2 to the fourth, that's 16. All right, so that's our x. But remember, we also have to get y. So we end up with a pair of points, 2 potential locations. When x equals plus 2, y would be square root of 2 times plus 2. All right, that's 2 root 2. And if we plug in x equals minus 2, we're going to end up with minus 2 times square root of 2. So that's minus 2. Oh, no, minus root 2 times 2. Okay. All right, still correct. Just a strange way to write it. Now, what comes next? The box, because we're done. All right, say what? We're done? When did that happen? Well, look at the problem. It says find locations. That's what we're after. The question asks us to find where the max or mins can occur. It doesn't say find which ones are max or find which ones are min. It just says, no, where should we be looking? Because that's what Lagrange multipliers helps us do. It helps us know where to look for solutions to our problems. And so we're done. Wow, nice, beautiful, beautiful problem. And even the answer is not so bad. You could even plug it in, and we get nice values out. But, we're not here to do that, because that's a whole nother can of worms. We don't need to open that. All right, well, let's do another problem. So, our next problem. Find the points which are nearest and furthest from the origin given 7x squared plus 3xy plus 3y squared equals 25. All right. Wow. Cool. Now, what do we have? Well, we look at this and we say, okay, we can see right away this kind of expression. We can call this g of xy, but really, this is our constraint. All right, great. So we know what our constraint is. So it's a constrained problem. We also know it's an optimization problem. And you might say, well, where does it say the word optimization? Well, it's here, ist and ist. Whenever you see words with an ist attached to them, that's really optimization. All right, we're trying to make things as near as possible. So we're trying to optimize nearness. As far as possible. So we're trying to optimize farness. So what don't we have yet? We know our constraint. We kind of have a vague idea of our optimization, but we don't have a formula for that. So we get to make one. Now, it doesn't mean we make one up. We have to say, okay, let's think about the problem. When we talk about near and far, we're talking distance. So we say, okay, our thing we're optimizing is distance to the origin, also known as 0, 0. So that's what we're after, trying to optimize our distance to 0, 0. And we should think of it as our point xy to our point 0, 0. Now normally, what would that be? That would be the square root of x minus 0 squared plus y minus 0 squared. Or you say, square root of x squared plus y squared. Could we use that for our optimization? Yes, absolutely. Wonderful function. Could we use something else? Yes, we can. And in fact, it's in our interest to do so. You might say, well, wait a second. There's only one distance. How could we use anything other than that? So here is a little bit of a and in fact, there's a nice principle in play. What do we know about the square root function? Well, it's a function which is called monotonic. And that's just a fancy way of saying it has one behavior. So if you were to plot it, it does that, right? It goes up. So what does that mean? Well, it says if you really want to make the square root of something as big or as small as possible, focus on the inside. So if you can make the inside large, that makes the whole thing large. If you can make the inside small, it makes the whole thing small. What's the general principle? Well, general principle says if you have some function, I'll say h is a function and it's monotonic, and then you say, look, if I'm trying to optimize the function h of something, all right, I'm running out of letters of the alphabet, I'll use k. To optimize h of kxy's, it's the equivalent to saying just optimize your k of xy. In other words, if you have a monotonic function, you can say just optimize what's inside. And that's because when you have a monotonic function, if you want to make it as large as possible, make the inside as large as possible, or as small as possible, make the inside as small as possible. It even works if your function is monotonically decreasing, and you just sort of have to do a small little adjustment in your mind, but it works out. Okay, if this doesn't make sense, then just go on faith for now. By the time you go in a couple years down the road, you'll be like, yeah, that was a good idea. I should have been using that for years now. Okay, so back to our regularly scheduled problem. What's our function? We're going to focus on the piece on the inside. So x squared plus y squared. So here we go. We want to optimize x squared plus y squared, given that 7x squared plus 3xy plus 3y squared equals 25. Okay, that doesn't sound so bad. That sounds like we could actually do it. Well, because we're going to. So set up our system of equations. Fx equals lambda gx. Fy equals lambda gy. Okay, well, that says f sub x is 2x equals lambda, and g sub x, 14x plus 3y. Fy, 2y equals lambda. G sub y, 3x plus 6y. And, all right, solving for lambda, 2x over 14x plus 3y is equal to 2y over 3x plus 6y. Cross multiply. And fingers crossed, nice things should happen to us. Because, you know, we're good people. We should expect nice things. 6x squared plus 12xy, right? Yes, is equal to what? 28xy. Wow. Plus 6y squared. Okay, well, maybe not exactly what we thought would happen, but, you know, we'll take it, and we'll keep working with it. All right, let's move everything to one side. So, well, let's move everything over. So 0 equals 6x squared minus, see, 12 subtract 28 would be 16xy, and then minus 6y squared. Okay, we can divide everything by 2. Okay, so let's do that. So we get 3x squared minus 8xy minus 3y squared. And now our chance to test how good can we factor. And, well, that should be a good challenge. Does it factor? And if so, how? Well, if it did, we could see, because there's not really many ways to break up 3, it'd have to be 3x and x. And now we say 3y. Well, it could either go into the first slot, 3y, or into the second slot. I claim it can't go there. If it did go there, notice that 3 would be common to both these terms, which means everything has to have a factor of 3. That doesn't have a factor of 3. So the only way the 3y could go is in that slot. Okay, so that says that would have to be a 3y. That would be a y. So that's the only way to get 3y squared. Now, we need to have one of them be plus and one of them be minus, because we end up with a minus here. And we need to make sure whichever one gets the larger one is the minus. Well, here, 3x times 3y, that's definitely larger. So minus and plus. So let's see, does that work? 3x squared, yeah, good. Minus 9xy plus xy, that's minus 8xy, minus 3y squared. It works. It's working. It's working. Nice. Okay. Well, what does that tell us? It tells us that, hey, there's really 2 possibilities. Okay, so we have either x equals 3y or y equals minus 3x. Those are the 2 possibilities, because remember, when these factor, they equal 0. So one of them had to be 0. Now, we're not done yet. These are our additional relationships. we still need to go back into our original constraint and use them to actually get points. So, well, we're going to get to do this twice. So for x equals 3y, all right, we get 7 times 3y squared. So that would be 9y squared. 3x would become, well, 3 times 3y would be 9y times y. So plus 9y squared and plus 3y squared. Okay, equals 25. All right, so remember, this is here. All right, so what do we have? We have a 63 plus 9 makes 72 plus 3 more makes 75. Y squared equals 25. And so that says what? Well, y squared is equal to a third. Or y equals plus or minus, I can write that as square root of 3 over 3. So that's what the square root of a third becomes. Now, plus or minus, because when we take the square root, we have two possibilities. And remember, x is 3 times that. So what will we have? Well, if we multiply this by 3, we'll get square root of 3, comma, square root of 3 over 3. And we'll get minus square root of 3, comma, minus square root of 3 over 3. All right. So those are some potential points. Now, we're not done yet, because that's if x equals 3y. What if y equals minus 3x? Okay, so we need to work on down. All right, so replace y by minus 3x. 7x squared. 3x times minus 3x would make it minus 9x squared. Right? 3x times minus 3x. And then 3y squared, well, minus 3x squared is 9x squared times 3. So that would be a 27x squared equals 25. Well, cleaning that up, 27 plus 7 is 34. Subtract 9, 25. So 25 x squared equals 25. Aha, x equals, well, x squared equals 1. So x equals plus or minus 1, which gets us to the following points, namely, what? Well, we would have 1, comma, and then multiply by factor -3. So 1, comma, -3, or minus 1, comma, multiply -1 by -3, you get +3. Okay, so we've ended up with 4 points. Now, here's the nice thing. These 4 points are our answers. We're not done with our problem yet, but how do we know they're our answers? Well, we know that there are answers because the problem asked us to do it, so there must be answers. It turns out this is an ellipse turned sideways. So there are definitely the nearest and furthest points. We also can see that the distance, for example, 1, -3, and -1, 3, they're the same distance away. Similar, these 2 points are the exact same distance away. So whatever their distances are, well, they're going to both be, these 2 are going to be equal and these 2 are going to be equal. And since we've identified all the potential places, well, 2 of these points are the nearest and 2 of them are the furthest. The only thing we haven't done is figure out which one is which. So let's just think about what happens when we look at x squared plus y squared, because that's what we're trying to optimize, right? Come back to x squared plus y squared. If we go here, our function x squared plus y squared would be 1 plus 9. So this would get our function equals 10 for those 2 points. Here, what would we have? Well, x squared would be 3. Y squared was a 1/3. So our function, which we're trying to optimize, is 3 plus 1/3, 10/3. And we say, okay, well look, 10 is bigger than 10/3. So these points are the ones which have a bigger distance. So they're the ones that are the furthest away. So here are our furthest. And these points have a closer distance. So these are our nearest. And there we go. We're done. We're done. Wow. What a fun problem. What a fun problem. And just things worked out so nicely. Yes. Ah. Wow. Good times. Good times. Well, I think we have time for one more. One more problem to finish us up. Our last one for this session. Find the maximum and minimum value of the function x squared plus 4y squared for a closed and bounded region of points satisfying 5x squared plus 12xy plus 20y squared is less than or equal to 64. Now you might say, whoa, oh, hey, Steve, slow down here. This does not feel like Lagrange multipliers. This looks like optimization on a closed bounded set. Well, it is optimization on a closed bounded set. So where does Lagrange multipliers comes in? We'll get to that in a second. Okay, so here we go. We're looking for the maximum. In fact, it's an absolute max and an absolute min because it's a closed bounded. We know it attains an absolute max and an absolute min. So the process, thinking back to when we talked about finding absolute max, absolute min, is we're going to make ourselves a list. Well, where do points on the list come from? Well, one place we check is the interior. So the interior is the less than part. In other words, we're not worried about the boundary. And we say, okay, we check the gradient and set it equal to 0. Well, the gradient of f is actually pretty easy. We can just do it. It's 2x and 8y. And if we set this equal to 0, we say, aha, this is corresponding to the point 0, 0, right? Because 2x has to equal 0, ay has to equal 0. So there is one place in the interior where our gradient is 0, and it's at the point 0, 0. So 0, 0 is on our list. Wonderful. Now, our boundary. Well, our boundary is what? Our boundary would correspond to the points where we have equality. So our boundary is 5x squared plus 12xy plus 20y squared is equal to 64. And here, it's not so clear what we can do. Because of all these extra pieces, it's not so obvious. How can we rewrite our function in terms of a single variable? So it's like, okay, this is where Lagrange multipliers is coming in. Lagrange multipliers is coming in to handle what's going on with the boundary. The boundary is acting like a constraint. And so we say, aha, now we see what to do. Here's our function, g of xy, and we proceed. So we're on the boundary, so all right, gradient of f equals lambda gradient of g, and what do we get? Well, f sub x equals lambda g sub x, f y is lambda g sub y. All right, well, okay, updating, that becomes 2x is equal to lambda, and then g sub x is 10x plus 12y. And then f sub y is 8y, and that's going to equal lambda, and take the derivative with respect to y, 12x plus 40y. All right, good. Well, progress, right? It is. We are making progress. So, next up, all right, solve for lambda. So, lambda is 2x over 10x plus 12y. but it's also equal to 8y over 12x plus 40y. Oh, well, cross multiply, and we're going to get 24x squared plus 80xy, yeah, see, is equal to 80xy. Wow, nice. Haha. Ah, we love it when that happens. Plus 96 y squared. 8 times 12, 96. And now we're like, wow, they love us on this problem. Because what do you see happening? The 80xy's cancel. Ah. Wow. Oh. And it even gets better. See, 96 is a multiple of 24. So we say, this is really saying that x squared is 4y squared. And that says, okay, you get x equals plus or minus 2y. Good. So that's an additional constraint. All right, well, now I got to dig in and see what happens. So let's explore our two options. Remember, two options are x equals 2y, x equals minus 2y. Everything right now we're doing, remember, is still on the boundary. We're still only making points on the boundary. And we're going to build up our list as we go along here. Okay, so on our boundary, x equals 2y. What will happen? Well, okay, so we're going to get 5 times 4y squared. That's 20y squared. Then we have 12 times 2y times y. That's 24y squared. And then here, 20y squared equals 64. Well, 20 plus 24 plus 20 is 64. So 64y squared equals 64. What? It's almost like they want us to solve it. I think they do want us to solve it. So y squared equals 1, which says, okay, really, y equals plus or minus 1. So we've now found additional points on our boundary corresponding to y equals 1, x equals 2 times that. So 2 comma 1. Our y is negative 1, and x is 2 times that. So minus 2 minus 1. All right, so that's points on our boundary where we see, okay, that's on our boundary critical. That's what Lagrange multipliers is finding. It's like, where are the interesting points to focus on with our constraint? And our constraint being, hey, stick to the boundary. Stick to the boundary. All right, well, I have to explore our other option. What if x equals minus 2y? All right, well, work it through. 5 times minus 2y squared, well, still 20y squared. Then we have 12 times minus 2y times y. That's minus 24y squared. And then plus 20y squared equals 64. And now, well, it's 40. Subtract 24 makes it 16y squared equals 64. Well, that's not so bad. Y squared equals 4. Okay, so what is y? Well, plus minus 2. So now these are additional points on our boundary where we potentially have maxes or mins. And so we say, okay, if y equals 2, x would be minus 2 times that, so minus 4 positive 2, and if it's negative 2, negative 2 times that, positive 4 negative 2. All right, whew, good. Now, we pause our Lagrange multiplier part of the problem because we're done with Lagrange multiplier. We've used Lagrange multiplier to identify where interesting points are. That's really what Lagrange multiplier does, is it says, hey, here are the interesting points. In the method of when we do absolute extreme, we say, okay, think about breaking into two parts, the interior and then the boundary, which we often say the corner and the bounding curves. So as a reminder, we said, okay, our bounding curve was kind of strange, so we thought about, hey, let's make that into a constraint and turn it into a Lagrange multiplier problem. Now we switch back into our, all right, we're making a list and checking it twice because we've made our list. Our extremes, our max and min values, have to happen somewhere in this list. So our last thing for us to do is to actually plug all of these points into our function f and see what comes out. Well, 0, 0 is really easy. We get 0. How about 2, 1? Well, we get 4 plus 4. That makes 8. And because we square, it's going to be the same thing for minus 2, minus 1, still 8. How about minus 4 comma 2? Well, that would be 16. And then 4 times 2 squared is 4 times 4 is another 16, which we put those together, gets us 32. Wonderful. And now we say, all right, which one is the smallest? And the answer is 0. So there's our min. Minimum value is 0. Which one's our max? Well, the 32. And it happens twice. It's okay to happen more than once. You can attain a maximum value multiple times. Perfectly, perfectly legal. And we're done. Because the problem says, what are the max and min values for the function on this region? And the answer, the min value you can get is 0. That was pretty clear. The max, 32. Maybe not so clear. But we did the work, and we got our answer. What a nice way to finish. What a great way to finish. All right. Well, hope you enjoyed Lagrange multipliers. It's a fun problem, learning to set up and solve our system of equations. Remember the general rule of thumb. When in doubt, solve for lambda. All right. Thanks for coming. Hope to see you again.